The topic of today's lecture will be about an application for image analysis and machine vision that you may be quite well aware of. Software that is able to be applied on an image of a scanned document or a photo that is made of a document, and the software should then be able to recognize characters on this document and translate it into a stream of ASCII character, coded ASCII characters. And I don't know about you, but at least I'm very curious about how these systems, how they work, and what kind of descriptors are applied, in order to be able to recognize the different letters. So I started to do some experiments, started to read about these systems, and I took help from a couple of master students that helped me to do a number of experiments within their project assignments. And basically this is what I'm planning to talk about today on this lecture. And the outline of my talk will be that I will discuss the fundamental steps of an OCR system. I will discuss the kind of training sets that I acquired using a simple scanner, document scanner. It will be training sets and testing sets with handwritten letters, written by hand, just by me, simply, and made a photocopy of this using the scanner. I will discuss the use of the classifier, and a very simple one called a minimum distance classifier, and I will explain how this simple classifier, how it works. I will discuss and explain to you how we made experiments and try to find different kinds of descriptors and combination of descriptors that are efficient in order to distinguish between different letters, and the analysis that we made on this area, and how we were able to improve the performance of the OCR classification. And in the end I will give you a summary of the performance of this OCR system. So as I said, I was using a very simple document scanner, as you see here, and I was making papers with simple printed characters printed by myself, and I made photocopies of this one. And the aim of this lecture is to show you how we were able to develop machine vision methods that could automatically recognize these handwritten letters and translate them into coded ASCII characters. And now I'm planning to present the different computational steps that were involved in the experiments that we did on the OCR system. And as I said to you before, the image acquisition, we did that one by using a scanned paper copy of hand-printed letters. What you can see here in the slide is the letter S that was written by hand by me, and it's being a scanned copy of the corresponding paper from the scanner, document scanner. The next step is that we perform pre-processing, and by pre-processing in this case we developed the gradient vector computed from the Sobel matrices. We computed both in the x dimension and in the y dimension, so that we have access to both the magnitude and also the directions. I will explain to you later on why. From this pre-processing we apply the segmentation by simply applying a threshold value, generating a binary output image. And this binary image then, where you have the light pixels, it means that for these pixels the gradients are the strongest. By labeling we are able to assign each one of these segmented components, being letters, assign them a unique code. It is visualized in this case by a unique color. The color may not look so unique for all the letters in this printout, but it is a unique code behind it. And when we have access to unique code for each one of the components, we then typically perform computation of some kind of feature. So the question then arises on what kind of features are to be computed for these letters in order to distinguish between them. And I'm not afraid of making different kinds of experiments, and you should also not be afraid of making experiments and think by yourself, you know, what could be a good descriptor in order to distinguish the different letters from each other. So I was starting to think from the fact that the gradient contains information about the texture and the shape of the letters. So why not try to apply an histogram of the gradient orientations corresponding to this edge histogram descriptor? Although the EHD, the edge histogram descriptor, is more known as a basic primary operator where we analyze texture on a local basis. But in this case, we are going to make experiments on applying the EHD on connected components. And this is one example of a letter and a computation of a corresponding EHD, where you see a ranging of 0 to 180 degrees and the probability of having this gradient then on the edges of the letter components. And based on this feature descriptor, we are then supposed to be able to perform a classification where we can associate this descriptor with a corresponding letter and generate on the output the corresponding ASCII code. And actually I'm quite curious on if we compute this edge histogram descriptor on connected components, how much will it be characteristic and how much will it distinguish between the different kind of letters? And I want to show you here on the first picture a training set of handwritten letters written by me of a set of R, and we have corresponding a set of B. And you see the corresponding descriptor that was computed from the gradients on each one of these connected components. It is computed on a histogram of having 9 bins here, 1, 2, 3, 4, 5, 6, 7, 8, 9, between the degrees of 0 to 180 degrees. And you have the corresponding probability on the vertical axis, and you have the degrees here on the horizontal axis. The difference between R and B is not that big, but you can still see that there is a slight difference. So let's continue and have a look at more of the letters. On this page you see training sets of the letters T and the corresponding of letters S, and I have also been using different scales. So you see that I have written the letters quite small and some of them are written quite large. And of course there is a certain variation also in the shape of the letters, since it's not machine printed, it's handwritten letters. And you can see here that you have a characteristic descriptor of the letter T. It is very much different from the letters S, I would say, in this case. So in my opinion it should be easy, even from just a manual visual inspection, it should be possible to distinguish between these two letters if you look at the diagrams here, which give me hope. It gives me hopes that this descriptor will actually work, and I'm not at all afraid of making a lot of experiments here, so you should not even be afraid yourself. Just try to make some experiments and find out what is a good descriptor and what is not. There is no right answer here. Just play around and try yourself, I would recommend. On next slide you will see the corresponding letter O and how the corresponding edge histogram descriptor will look like. And if we summarize all of them on one page, then so you have R, B, T and S and O, handwritten of course. So you see how they are quite different, but of course, yeah, it's not that big difference between R and B. may not be that big difference also between O and B, but at least between S and T it should be easy to make a difference, even manually, by just having a look at them. Yeah, so the question is, like, if we apply then at the last phase here a computerized classification step, whereas we want to have a good decision on this descriptor and how it looks like, what should be the corresponding output ASCII character, and try to find the highest probability of having a decision in a classifier that is the correct one. This is what we are going to analyze now. And for the classification we used the minimum distance classifier, and I think it could be a good idea that I give you an introduction to this simple way of doing the classification before we analyze the performance of the OCR application. So in this picture you see a three-dimensional feature space, and you see 5 classes, clusters of data in this score plot, or scatter plot, I should say, scatter plot of feature vectors, and the feature vectors are then centered around a class that corresponds to a class. And then the way of doing the classification for an input feature vector that comes, it's computed and comes into the classifier, is that for this feature vector that we call x, then we compute the distance from the position of this feature vector to the centroids of all the classes, and we select the shortest distance from vector x to the class to be the one that are selected for the output class of the classifier. So the shortest distance, that class is selected to be the one that is the output of the classification. I have also included a reference here that you can search for on the research databases and read more about minimum distance classifier. I'm also planning to give you a formal description of the computations being performed in this classifier. So what we have here on this picture is an equation showing a sample space for class K, and K is belonging to a set of classes of S number of classes, 1 to S, and we then have a number of samples that is belonging to this class, and we have NK number of samples. XIK is then the eth sample feature vector, so it's a feature vector that is belonging to class K, and I is then belonging to 1 to NK, and NK is then the number of samples that are associated with class K. And for each one of the feature vectors we have features ranging from 1 to M. So it means that one of these feature elements here, XIJK, is the eth feature in eth sample for class K, where then the feature belonging to one feature vector is indexed by J, belonging to 1 to M number of features for one feature vector. RK is then a reference vector. It's a centroid position for each one of the classes that are computed. So it's a mean value for each one of the features computed over all the feature samples, and it's being computed for all the classes K belonging to 1 to S, class number S. And as I will show you on this picture, this RK, this reference vector, corresponds to then the centroid of each one of the classes, where K is then indexing this class. And when we are having a feature vector X that is coming into the classifier, you know that we are computing the shortest distance to each one of these centroids and selecting the one that is closest. The mean value for feature J, a mean value that is computed over all the nk number of samples and computed for class K, is corresponding to this equation. And this is the way of computing the mean value features for all the features belonging to the reference vector RK. Then an input vector that comes into the classifier, the vector to be classified. What we need to do is to compute the distance to all the reference vectors RK. We compute the distance dki according to this formula. We do it with respect to each one of the features, and we compute the Euclidean distance. Then an input vector xi. It is classified as belonging to class C if xi is belonging to class C if the distance from the input feature vector x to class C is the minimum, the smallest one, if it is computed for all the classes K. If it's the minimum, then we make the decision that the input vector xi is belonging to the class C, which is then the output of the classification. So after giving this review on the theory of a minimum distance classifier, I would like now to come back to the problem of the OCR system and what happens when we apply this simple classifier to the edge histogram descriptor that we have chosen as a feature to be included for the OCR system. Let me remind you about the picture I showed you previously about the corresponding diagrams for the edge histogram descriptor for the handwritten letters R, B, T, S and O. And you see here, for instance, that the R and B, they look pretty much similar. So what happened is that I prepare in a similar way a test data input by writing this letter by hand and scanning them in a scanner and running them in the same system as has been used also for training. And then you, after applying the minimum distance classifier, you see the corresponding series of characters that were chosen at the classification step. And not to be surprised, we can conclude that there are problems to distinguish between the letter B and R. So two B's here, the second B is for some reasons interpreted as the letter and the character R. From this point I discussed this problem with a couple of master students who wanted to make their 15 credit points project and having a good assignment. So I asked them to investigate this problem and see how it can be improved and what other kinds of features then possibly could be included into the computation in order to make the performance to be much improved, to get rid of this problem. And what they started with is to, in their experiment, they extended the number of bins in the edge histogram descriptor from 9 to 15 bins, and they also extended the degrees range from 0 to 180. Instead they are using 0 to 360 degrees. And by doing this adjustment they could end up in handwritten letters ranging from A to Z at a success performance of 70% success rate. And this was done by these students. You have the reference down here written on the slide, and the name of their report: Hardware-Centric Original Character Recognition. They continued their work. What we see here on the slide is the extended feature vector for B and R, showing 15 bins. They are still looking quite similar. But then what they did is that instead of using hand printed letters, we are trying to apply it, on machine printed letters. So this graph that you can see here is corresponding to 15 bins and for machine printed letters. And not to be surprised, there was an improvement, of course, in the performance from previously 70% on the handwritten letters, now to 87% success rate on the machine printed letters. But still they experienced problems on the letters R and B. They are still hard to distinguish between. So the question now arises, what more of features can we add to our feature vector that is corresponding only of the edge histogram descriptor? What more of geometrical features that describes in a good way the properties, the geometrical properties of the characters can be added to the feature vector? And in particular to solve the problem with the problematic letters R and B that we obviously have problems with. So the first feature that my students made experiment on is measure of the eccentricity of an image component, which means that we want to measure the displacement vectors between the center of a bounding box. The bounding box is the smallest box that encloses surrounding the image component, and the corresponding centroid that is computed for the image component. This displacement vector is described in the vertical dimension and in horizontal dimension separately. And if we also, in addition, we relate these displacement vectors with respect to the size of the bounding box, we can make this feature independent of the scaling of the image component, which is a property that we really want to have for a feature. The next one my students made experiment on is a zonal histogram. Then again, based on the definition of the bounding box, the smallest box that encloses the image component. And within this bounding box we define 4 of these zones, these areas, and we compute, based on a training set, the probability of having a pixel residing within these zones. And then based on this information we get a good feeling. It adds on a good feeling for the geometrical property of a letter. And it adds 4 additional features here for this zonal histogram. And we added 2 more features from the displacement vectors of the eccentricity. So altogether we have now added 6 more features to the feature vector. And now we have computed it again for our problematic letters B and R. And I think that if we just make an ocular inspection, a manual inspection on the shape of these diagrams corresponding to the feature vector for B and R, I think it should be possible even for a human, based on these diagrams, to make a difference between letters B and R. So I would expect that classifier should perform pretty well, using this added information that we have done here now. So when we did the experiments using the minimum distance classifier, so after adding these zonal histograms and the eccentricity vectors, the classification success rate improved up to 86% for handwritten letters, and it was even close to 100% for machine printed letters. And if you summarize the outcome of all the experiments that was made on this OCR system, we have this table here showing a summary. And in the beginning, for using only the edge histogram descriptor and on handwritten letters, we achieved a success rate of 70%, and for machine printed letters correspondingly 87%. But then, as I described throughout this presentation, we added the features to the feature vector corresponding to these geometrical properties of letters. For handwritten characters, we had an improvement up to 86%, and for machine printed letters we ended up at a success rate of very close to 100%. And I believe that this is the kind of performance that we would like to have for a reliable and robust OCR system. And all of these experiments that I described today was mainly done by my two master students on their 15 credit points project assignment under supervision from me, and they entitled their work Hardware-Centric Original Character Recognition. And from this lecture, I really do hope that I have inspired you to do additional experiments on automatic recognition of objects, on OCR systems, and on machine vision. I thank you for your attention, and I hope to see you again here on my next lecture. But anyway, thank you for your attention today. Bye.